you ever stopped to think about what keeps our digital world from just collapsing? Seriously, every single time you buy something online, move money between accounts, or book a flight, there's this powerful, completely invisible set of rules working in the background, making sure nothing gets lost or messed up. So today, we're going to pull back the curtain and explore the secret engine that powers our modern lives, the database transaction.
So, here's our game plan. We'll start with the absolute basics. What even is a transaction? Then, we're going to get into its 4 superpowers, also known as the ACID rules. After that, we'll see what happens when these transactions start bumping into each other in a high-speed, kind of chaotic environment. And finally, we'll look at how these systems are built to survive pretty much any disaster you can throw at them.
All right, first things first, let's talk about what a transaction is. And nope, it's not just about money. In the world of databases, a transaction is the most fundamental unit of work. You can think of it as the atom of any reliable digital process. It's the very thing that builds trust into the system. I mean, really think about it for a second. When you send your friend $20, a whole bunch of things have to happen, and have to happen perfectly. The money has to leave your account, right? And it has to actually arrive in their account. What's to stop it from just vanishing into the digital ether if your phone battery dies halfway through? Well, the answer to that is the transaction.
Okay, so here's the official idea, but let's break it down. A transaction is basically a package of operations, reading some data, writing some data, that all have to be treated as one single unbreakable unit. It is an all-or-nothing deal. It either succeeds 100% or it fails and the database is left exactly the way it was before you even started. No in-betweens.
Let's make this super concrete. Say you want to transfer $50. The system runs through a series of steps, just like these. First, it reads your balance, subtracts the $50, and saves your new lower balance. Then, it reads your friend's balance, adds the $50, and saves their new higher balance. Now, what happens if the power goes out right after step 3? Well, without a transaction, that $50 would be gone from your account, but not yet in your friend's. It'd be lost. But because this is a transaction, the system sees it didn't finish and just undoes the whole thing. It's like it never happened.
So how does a transaction actually make these incredible guarantees? Well, it follows a very strict set of 4 rules, and they're famously known by the acronym ACID. And trust me, these aren't just suggestions. They are the fundamental laws that make our data-driven world even possible.
These 4 properties are atomicity, consistency, isolation, and durability. Let's dive into each one of these superpowers and see exactly how they work to keep your data safe.
First up, we have atomicity. This is that all-or-nothing rule we've been talking about. The name says it all. A transaction is like an atom. You can't split it. For our money transfer, this means you simply cannot have the money taken from account A without it also being added to account B. The entire transfer is one single atomic action, period.
Next, we've got consistency. This rule is all about making sure a transaction doesn't break any of the database's own internal rules. For instance, let's say a bank has a rule that no account balance can ever go below 0. Well, a transaction that tries to withdraw more money than you have will simply fail. The database must always move from one valid logical state to another. In our example, the total amount of money across both accounts is exactly the same before and after the transfer. It stays consistent. Okay, next up is isolation. And this is where things get really cool. At any given moment, there could be thousands, even millions, of transactions happening at the same time on one system. Isolation means that every single one of them is sealed off from all the others, running in its own little bubble. So my bank transfer, while it's in progress, is totally invisible to your bank transfer until mine is 100% finished. This rule is what prevents complete and utter chaos.
And finally, we have durability. This one is the ultimate promise. It means that once the system gives you the thumbs up and says your transaction is complete, that change is permanent. It's written in stone. It will survive a power outage, a server crash, pretty much anything. Once you get that transfer complete message, you can rest easy knowing that change is safe and sound forever.
Okay, so isolation sounds amazing in theory, right? Everyone gets their own little bubble. But here's the catch. To make things run super fast, databases don't actually wait for one transaction to finish before starting the next. They cheat a little. They interleave the steps, mixing and matching operations from different transactions to save time. And if this isn't managed perfectly, things can go wrong in some really spectacular ways. Let's take a look.
This is what we call the classic lost update problem. Just follow the timeline here. Transaction T1 on the left reads the number of available seats on a flight. Let's say it's 80. But before T1 can finish its job, transaction T2 on the right also reads the number of seats, And guess what? It also sees 80. Now T1 books 5 seats and writes back the new total, 75. But T2 has no idea that just happened. It's still working with the old number, 80. So it adds 4 seats from a cancellation and writes back 84. Poof. T1's update is just gone. It's been overwritten, lost forever. And now the airline's count is dangerously wrong. And this one? This one is even scarier. It's called a dirty read. Here's how it works. Transaction T1 makes an update, but before it can officially save or commit that change, transaction T2 sneaks in and reads that brand new temporary value. But what if T1 then fails for some reason and has to be rolled back? Well, now T2 has seen and maybe even made decisions based on data that technically never existed. It's like making a huge investment based on a hot stock tip from a friend who then calls you back and says, actually, never mind. It's bad news.
And finally, we have the incorrect summary problem. This one's a bit more subtle. Imagine a third transaction, T3, whose only job is to calculate the grand total of reservations. It reads the number of seats from account X after T1 has moved some seats out, but then it reads account Y before T1 has had a chance to put those seats in. So the final sum it calculates is completely off, because it's looking at a snapshot of the database that never actually existed all at once. It's a phantom state.
So you might be thinking, with all these potential ways for things to go wrong, plus the constant threat of system crashes, how on earth do these databases stay reliable? Well, they are built from the ground up with one thing in mind: recovery. They're designed to be reliable in a fundamentally unreliable world. And when we say failure, we mean everything and anything. It could be a simple software bug, like trying to divide by 0. It could be a local error, like trying to withdraw money that isn't there. It could be a hardware crash, a disk that just dies, or even a full-blown physical catastrophe like a fire or a massive power outage. A truly robust system has to be ready for all.
To manage all this, every single transaction has only 2 possible fates. That's it. It either reaches a successful conclusion, which we call a commit, and its changes are made permanent, or it ends unsuccessfully, which we call a rollback or an abort. And if that happens, any changes it was trying to make are completely wiped away, as if it never even began.
You can actually map out this whole journey. A transaction starts out in the active state, doing its work. If it gets all its steps done successfully, it moves to partially committed while the system does a final check. If that's all good, boom, it's committed, and its job is done. But if anything, and I mean anything, goes wrong along the way, it immediately gets shunted over to the failed state, and all of its work is rolled back. And this quote right here, it really just says it all. This is the core promise of any transaction processing system. It's a solemn vow that it will either do everything you asked for, perfectly and permanently, or it will do absolutely nothing at all. There is no messy middle ground.
Okay, I know this has been a bit technical, but let's bring it all back home. Why does any of this matter to you in your day-to-day life? What's the real impact of all this behind-the-scenes logic?
Well, it really boils down to this. These ACID properties are the invisible foundation of trust for our entire digital economy. They're the reason you can feel confident that your online payment actually went through, that the concert ticket you just bought is actually yours, and that the bank isn't just randomly misplacing your money. It's all about ensuring correctness and fairness for everyone, every single time.
And that leaves us with one last really fascinating question to think about. We've just seen the incredible amount of logic and safety checks that are built into just a single transaction. But modern systems, for things like stock markets, airlines, or giant online retailers, they handle millions of these every second. So how in the world do they do that at that mind-boggling speed while still guaranteeing every single one of those ACID rules we just talked about? Well, that is a story for another day.